Hello, everyone. My name is Arthur Tsang, and I'm here to talk about the small-scale structure of interlopers. This talk is based on work that I did in Cora Dworkin's group at Harvard, along with John Schengel and Ana Diaz-Rivero, with additional collaborators at Berkeley, Hongming Chu, and Urosh Seliak. This talk is based on the paper quantifying the line-of-sight halo contribution to the dark matter convergence power spectrum from strong gravitational lenses at the archive link given here. First, we will talk about the motivation. Then we will go into the relevant previous work about lensing and interlopers, which are also known as line-of-sight halos. Then we'll talk about methods, results, and the conclusion. So first, for the motivation. As you know, lambda CDM has been well measured on larger scales with the CMB and LSS and so forth. However, on smaller scales, it's trickier to test and has not yet been well constrained. Because of this, most of what we know about dark matter comes from the larger scale observations. So having better constraints on smaller scales, like 10 to the 8 solar masses or smaller, which corresponds to dwarf galaxies roughly, this would help us a lot to distinguish between the currently plausible dark matter models. So for example, here's the predicted mass function for cold dark matter in a plausible warm dark matter model. The mass function is just the abundance of structure at a given mass. So notice how they are similar at higher masses over here, but they differ greatly at lower masses. This means that observations for lower masses will be very helpful to distinguish between different dark matter models.
So why are there no clear constraints yet? Well, one reason is that the halos that we want to observe are small, and so they will have a low rate of star formation, and thus they will be dark and difficult to observe. However, it is possible to make local measurements, and here we run into another problem, which is called the missing satellites problem. So basically, the number of satellite galaxies that we measure is smaller than what we would expect from lambda CDM. Does this mean that lambda CDM is wrong? Well, maybe, but it's also possible that the rate of star formation is so small that these smaller halos are effectively invisible to us. Or possibly there's an effect called tidal stripping, which eats away at the mass of a halo, and the extent to which this happens is not well quantified.
So the solution that we're going to look at for the rest of this talk is to use gravitational lensing. Gravitational lensing is very helpful because it allows us to bypass this problem about the structure being dark, since the gravitational lensing is only sensitive to the mass of these halos itself. All right. So going on to previous work in lensing, we can study this small-scale structure as perturbations to a strong lensing system. Here, strong means that we get multiple images of the same source, and this allows us to model the lens mass distribution relatively accurately. So note there are two types of such systems that we can look at and that have been successfully studied in the past. One of them is the quadruply imaged quasars, also known as quads, such as shown in this figure at the top left. And then the other is galaxy-galaxy systems, such as that shown at the bottom left,
where the main lens is a galaxy, and there's also a galaxy as the source.
So now, what makes these kinds of studies a bit tricky is that what we're really interested in is the convergence field, which you can think of as just proportional to the mass in the case of single-plane lensing. And if you look at the small-scale structure of this field, you can analyze it as subhalos. However, it's not directly observable.
There are ways to get around that, though, using certain constraints of how a strong lensing system can look.
It has been demonstrated that a larger individual subhalo has been found, and it's also possible to measure the statistics of smaller subhalos even if you can't individually find any single one. So to elaborate on these statistics, this figure on the left over here shows an example of what the convergence due to subhalos might look like, and this figure on the right shows what the corresponding power spectrum might look like. So what this statistical result was saying is that even though we can't measure the figure on the left, we can still make some rough measurements of the figure on the right, and this would give us information about the subhalo mass function and subhalo parameters, such as what kind of profile it is, maybe T, NFW, or something else, and the characteristic radius. So this can already start telling us things about dark matter, even if we can't find a single individual subhalo. All right. Now, meanwhile, there's been previous work on interlopers, or the line-of-sight halos. So what these are is basically when you have a system with an observer and a source that are thousands of megaparsecs away, there's going to be some structure in the middle. And so this structure will perturb the lensing slightly. Not very much, but on roughly the same order that subhalos perturb the lensing. And so this means that, that any analysis of subhalos should also take interlopers into account if there are enough of these interlopers. And so what a previous study has found is that there seems to be a mass redshift degeneracy, which means that different interlopers at different redshifts, so different values of the x-axis, look a lot like different interlopers at different masses. So in particular, what this means is that an interloper produces deflections that are similar to that of subhalos, even though it might be a subhalo of a different mass. All right. And so now the next question is, are these interlopers actually common? And the answer is yes. This study and another study has found that the raw number of interlopers is actually greater than that of subhalos. Depending on the exact details of the system you're looking at, they found between about a factor of 2 to a factor of 10 in favor of interlopers. So this means that we really need to go back to any study which assumes that all of the substructure or all of this perturbation came from subhalos, and really re-examine that to see if it might be from interlopers instead. All right. So now it's time to go into our own methods. So the probe we use is the convergence power spectrum of interlopers. So what we do is we first develop a theory to quantify it analytically, then we confirm this theory with numerical ray tracing, and then finally, we compare the power spectrum of interlopers to the power spectrum of subhalos to see the relative strength, which is not necessarily the same as the relative numbers. All right. So first, for the case of single plane lensing. So you can see in this diagram, the light comes from the source over here. It gets bent at the lens by an angle alpha hat, which is based on the mass distribution at the lens, and it arrives at the observer over here. Now, the observer observes it to be at a position, at an angular position x1, so it looks like the image is here, although really the source is over here. And we call the difference in this position the deflection angle, alpha, and this goes into what is called the lens equation, which basically just says that the 2D angular source position, y, equals the image angular position, x1, minus the deflection angle, alpha. All right, so this is good as long as the lens obeys the thin lens approximation, which basically just says that the thickness of the lens should be much smaller than the distance between the observer and the lens, or the lens and the source. And so, of course, this is true when we're just looking at subhalos, but if we want to include interlopers, this breaks down. So this is where we go on to the generalization, which is multiplane lensing. So now the multiplane lens equation traces rays backwards, starting at the observer and tracing the position through every lens plane until we get to the source. And so this is useful because now we can solve for the effective convergence. So the question we're asking is basically, how can we replace the convergences of all of these multiple lenses with a single convergence field at the main lens plane, which produces similar deflections? And the way we answer this is by taking the derivative of the lens equation. So in the case of single plane lensing, we take the derivative of the source position divided by the image position. And since this was a 2D vector equation, we get a Jacobian that looks like this. And the convergence is just the average of this diagonal component over here. So now, because we have this alternative definition of convergence, this definition is also applicable to the case of multiplane lensing. So we can take the same derivative over here, and we get the sum of contributions from the foreground lenses, the main lens, and the background lenses. And so from here, after doing some algebra and applying an approximation called critical Schritt-Born, or CSB, this approximation just says that we integrate the deflections along a light ray which is deflected only by the main lens. But the important thing is, after we do this algebra, we get an equation for the effective convergence in terms of the weighted sum of the convergence at every individual redshift plane. And this is interesting because it allows us to analytically solve for interlopers as effective subhalos.
So the results in the literature were really just numerical fits.
But now we have actual expressions for the effective radius as a function of redshift and the effective mass as a function of the redshift as well. And this leads us to the interloper power spectrum. So we have two equivalent ways to derive it. One of them is by taking the 2D density as an integral of the 3D density with the kappa effective weighting that we just derived, but otherwise following a weak lensing formalism. An equivalent way of deriving it is to first project all of the interlopers onto the main lens plane as effective subhalos, and then to Fourier transform the 2-point correlation to get the power spectrum from there. Either way gives us the same analytical result. And the things I'd like to point out here is that there's a term for the key effective weighting as well as the 3D to 2D density conversion. It also depends on the mass function. So this makes sense because the more interlopers we have, the more of a power spectrum we expect to get. And it also depends on the profile. So this would be the effective profile, such as NFW, which is scaled with the effective radius scaling. All right, so this is good. Now we have an analytic prediction for what the power spectrum should look like. Now we had to make a couple of analytic approximations to get there. So in order to check that this is valid, we also do a numerical calculation. So here we use a Python package called Astronomy, which can do multi-plane ray tracing. So this means it is not making the critical sheet-born approximation anymore. It is actually doing the full ray tracing. It's not doing any of those projection effects. And from here, we can calculate deflection angles. And from the deflection angles, we can get another effective convergence. This definition is actually the same as the one we were using before with the Jacobians. So then what we do is we make a fiducial lensing system, and then we simulate it at 2 resolution scales. We do 2 resolution scales just so that we have a wider degree of different length scales that we can probe while keeping the resolutions computationally manageable. So you can see that in this picture. The picture as a whole is the large scale, and this zoom up orange box is the smaller scale for the finer details. Also to note is that we take the annular mask at large scales rather than just naively taking the power spectrum of this whole image. And that is because the statistical properties, as we get far away from the Einstein ring, which is shown in white over here, the statistical properties there get very different. And so they would change the results. Also note that any probes that we use in the real world would not actually be sensitive to substructure or interlopers far from the Einstein ring, because the Einstein ring is where the light is. All right, and then so finally we get to the results. We got some analytical formula. We did a numerical simulation. And so the first thing to do is to see how well they match. And indeed, they match very well. So the 3 different colors shown here are the subhalo power spectrum, the interloper power spectrum, and the combined subhalo plus interloper power spectrum, which is what we would actually measure. And you can see the dotted lines are the analytic predictions, and the solid lines are the numerical results. So you can see they fit very well. The residuals are smaller than the errors that we would have on any actual power spectrum measurements. Also just to note, in order to get actual numbers, we had to make some choices for a fiducial system. And in this fiducial system, it turned out that the power spectrum of the interlopers was roughly 7 times as much as the power spectrum of the subhalos. This is not necessarily the case, though. So in order to study how this changes how the relative strength of interlopers and subhalos changes as a function of different systems, we focus on the plateau of the power spectrum curve. So that's that flat limit on the left of the graph. And so what we can vary are the redshifts. So we can change the lens redshift and the source redshift. And we can also vary the mass functions. So there are two mass functions. One is the mass function of the interlopers, better known as the Halo mass function. And for that, we can use Press-Schechter or Schacht-Thorman. They're a little off of each other, but not by too much. And then the other mass function is the subhalo mass function, where it fits a power law, which is pretty well constrained, but the actual normalization is not. So we write this normalization with a parameter we call f sub, which we define as the mass of as the total mass in subhalos divided by the total mass in dark matter, and we see how the subhalo or interloper power plateau varies with respect to that. All right, so this graph shown here shows the plateau for the interloper, the plateau for the subhalo, and then what I find most interesting, the relative subhalo to interloper plateaus. So you can see over here, the bluer it is, the more subhalo dominated your signal is, and the redder it is, the more interloper dominated your signal is. And this makes sense because at all of these dots, which correspond to real-world gravitational lensing systems, which have already been found, and as we increase the source redshifts, the interlopers become more and more prominent, which makes sense because there's more space that you can find interlopers in. All right, and as we were saying on the previous slide, this f sub normalization of subhalos is poorly constrained. This is because there's an effect of tidal stripping, which we talked about earlier with regard to the missing satellites problem. And the problem is that tidal stripping is not well quantified with or without baryons. So in the literature, most of the values of f sub that we found were on the order of 10 to the minus 3 to 10 to the minus 2. And so we made an online widget, which is basically a version of the graph from the slide before, but where you can play around and test out different values of f sub. So what we find is that at a very low value of f sub, our signal is completely interloper dominated everywhere. At around 2%, then it starts to become equal for these lenses over here, which are characteristic of the SLACS lensing catalog. And at an f sub of 4%, then the interlopers and subhalos start having equal contributions at BELLS. All right, so in conclusion, we wanted to test lambda CDM on small scales. So to do this, we focused on perturbations to galaxy-galaxy lensing systems. We expect more line-of-sight interlopers than subhalos, according to previous studies. And now we introduce a new probe, the interloper effective convergence power spectrum. And we find that as long as f sub is less than about 2%, the interlopers will dominate for SLACS-like lenses, and likewise for 4% for BELLS. And the simulation suggests that it's quite likely that f sub is smaller than this amount. And so reflections in future work. This is good news if interlopers dominate over the subhalos because it's a stronger signal. And more importantly, the theoretical mass function of interlopers is better understood, so it will be easier to connect the theory and experiment.
So for our next step for future work, we're interested in how we can extract information from the curl of the deflection angles. So even though we didn't talk about that much here, basically in the case of single plane lensing, you only get a divergence component, but not a curl. But as soon as you start adding interlopers, then you do get a small curl component. So we're looking into how we can use that to distinguish between interlopers and subhalos. All right, thank you for watching, and hopefully see you at the discussion session. Bye.